Section 1.4, we're taking a look at trigonometry. What's that? This isn't a math class, I hear you say. Well, it turns out math is the foundation of everything, even physics. It gives us useful tools to describe the world around us. So as part of our building blocks, we're going to get into some of the tools of trigonometry, and we will use it quite a bit in a lot of our physics examples. So trigonometry we'll use anytime we have triangles, but also when we have something called vectors, which we're going to see in the very next section. We'll be able to break down vectors into components using these trigonometry ideas. First off, we'll focus on triangles though. So a triangle has three sides. That's a good start, right? And the longest side of the triangle is always called the hypotenuse, right? Especially if it's a right triangle. And this class, we basically only focus on right triangles. So that's just the right way to think about this, that we'll have a right angle or 90-degree angle within our triangle, and there will be some other angle of interest. You technically can focus on either of these two angles, but we just happen to pick the one down here, and we called it theta, which is a Greek letter that's often used to represent the angle. So the hypotenuse is the long side that is opposite the 90-degree angle. And then there's two other sides. There's the adjacent side, h sub a, which is the length of the side that is adjacent to this angle theta. And then there's the opposite side, which is noted with this h sub o, the length of side that is opposite angle theta. So we need these side lengths, ways to describe the pieces and parts of the triangle. And once we have those defined, then we can go back to my favorite SOHCAHTOA, right? Sine, cosine, and tangent. Maybe you've already seen this before. If so, then this is just a review to make sure we're all on the same page. If you haven't, then please make sure to pay extra attention because we will be using these trig functions all semester. So when we use this sine function and we take sine of that angle theta, that ratio is equal to the opposite side length divided by the hypotenuse. And so the way that I remember this, and you can write this on your note sheet, or you can just write the full formulas out, is as so, right? Where sine is equal to the opposite side divided by the hypotenuse side. For cosine, when we take the cosine of the angle, that's going to be equal to the adjacent side, A, divided by the hypotenuse, H. So that's where we get the ka, so ka. And then our last one is tangent, and that one does not involve the hypotenuse. It involves the opposite side and the adjacent side. And it is the tangent of the angle is equal to the opposite side divided by the adjacent side. So that's where the TOA comes from. And so that describes these three formulas. And trigonometry, these relationships of sine, cosine, and tangent, relating the angle to the side lengths of the triangle, can help us out in a number of situations. So here's one example of using trigonometric functions to figure out the height of a building. You can actually try this out. I encourage you to do it if you can come up with some measurements in order to do this. In this case, it says, on a sunny day, a tall building casts a shadow that is 62.7 meters long. The angle between the sun's rays and the ground is 50 degrees as shown in the figure. Determine the height of the building. Right, so as we're looking at this, we say, hey, there's the sun, it's shining on the building, and the building is making a shadow, which is noted in the gray here, that's 67.2 meters. And it also tells us this angle of 50 degrees that is between the sun's rays, the diagonal, and the ground, which is the horizontal. So that allows us to have labeled that we know this angle, that's our theta, that's 50 degrees. And then we also know this side length. Now we want to label these things in terms of our known quantities. So if that is our theta, and we know that our right angle is over here in the corner, then what would we call this side length? Well, this is the one that is right next to the angle theta without being the longest side of the triangle. This would be our hypotenuse up here. So the close one is the adjacent, h sub a. Now, what are we trying to solve for though? We know the angle theta, we know our adjacent side. We want to find the height of the building. Now, it would be easy to look at this and say, hey, look, I have an H on the page, that's probably for height, cool, and solve for this. But this would just be the length of the diagonal, not the height of the building. So the height of the building, note, is this other direction going up alongside the building. And so in terms of the triangle, I would label that not as H, but as the opposite side to the angle, H sub O. Once I've identified that, then I can focus in and say, hey, look, I want to find HO, and I know HA, and I know my angle theta. So I want a trig function that combines those three parameters. So opposite, adjacent, and angle. Think for a moment about which trig function it is. It is tangent if you said that. So tangent of theta is equal to the opposite over the adjacent. And here we're solving for the opposite, so what I'm going to do is multiply both sides by the adjacent side. So that means that my final equation will be that H sub O is equal to the adjacent side, HA, which is 67.2 meters, times tangent of theta, where the angle theta is 50 degrees. So let's check this out. The next slide. So here we have the final work, right? And they plugged in numbers before multiplying across. If you prefer to do that, that's totally fair, right? I worked with symbols instead because this is a more general result that will apply regardless of the length of the shadow or the angle in there. But if you plug in the proper numbers, you come out with 80.1. And notice the units are going to come from that adjacent side, the 67.2 meters. That means we're left with meters. When we take tangent of an angle, that's no units. So we don't need to worry about that contributing any units here. All right, so that tells us the building is 80 meters tall, which is quite tall. And that illustrates how we can use the angle and a side length to get the other side of a triangle. Now there will be some times where we know the side lengths, but we want to find the angle. And in that case, we can use the inverse trig functions in order to find the angle. So when we take the inverse of both sides, we take sine to the -1. This is not the same as 1 over sine. That's not what we want to think of here. This is just an entirely different button on your calculator. You often have to hit second to get sine to the -1, or if you're typing out on a computer, you can type it out as arc sine. But it's the way to undo the sign that was on this theta, and we're left with undoing the sign on this ratio of side lengths. And so that's a way that we can solve for the angle. And let's try an example of this. Example 5, using inverse trigonometric functions. A lakefront drops off gradually at an angle theta below the horizontal. For safety reasons, it's necessary to know how deep the lake is at various distances from the shore. To provide some information about the depth, a lifeguard rows straight out from shore at a distance of 14 meters and drops a weighted fishing line. By measuring the length of the line, the lifeguard measures the depth to be 2.25 meters. What is the value of theta? Right, so here's an example where it really helps to draw a picture because they didn't happen to give us one. And that's where we have to look at the text and try to put it into picture form. Take the words and put them in pictures. So the lakefront drops off at some angle below the horizontal. So I'm picturing that we have a lake here. This is roughly horizontal. And then we have a shoreline, right, where there's land, cool. But then as the water starts, the lake front, the floor, is dropping off at this angle below the horizontal. So now I'm going to label this as my angle theta. And this is the key, some of the hardest part to get in the picture. All right, so now that we have that, It says that the lifeguard rows straight out from shore at a distance of 14 meters. So we could put a little boat here with a lifeguard. And we know the lifeguard has rowed out from shore this distance of 14 meters. So I have to ask, is it going to be labeling the lower, the brown side, or the top side? Well, it's what the lifeguard measures. The lifeguard isn't walking along the bottom of the lake, so it's just this distance that is top side. That will be my 14.0 meters. And at this point, it says the lifeguard drops a line, measures the depth to be 2.25 meters. So depth of water going straight down, that shows how deep it is, 2.25 meters. Awesome. This is the hardest part of the problem, was creating this picture. And so this is what's going to be a challenge in the homework. So I encourage you to be very deliberate in drawing pictures. It will help you out. Now, if we think about this, we want to find the angle theta. In terms of these two side lengths, notice we have a triangle now, right? We have the horizontal distance, the vertical distance. We just don't have the lakeside shore distance. And notice this is the longest distance. So this is going to be our hypotenuse down here. So we want a trig function that does not involve the hypotenuse, and we'll use the inverse of it. So which one would that be? That's going to be our tangent. That our angle theta is equal to inverse tangent of our opposite, the 2.25 meters, divided by our adjacent, the 14.0 meters. And what you'll notice is that because we have meters divided by meters, those meters are just going to cancel out. And we're left with the inverse tangent of this fraction, which is how tangent should be. And that's because we're not going to have units within the tangent. Now, our final answer here is going to have units, and those units will depend on what mode your calculator is in. So if your calculator is in degrees, then you should get, at this point, 9.13. But if for a math class, your calculator is in radians, you'll get a different answer. So that's something you want to check within your calculator, is what mode it's operating in. And make sure that you get this 9.13 degrees. We'll often be working with degrees, at least for these first few chapters. It's only with rotation that we'll start caring about radians. All right, so checking the work. They show a nice picture here, and they come out with that 9.13 degrees. One more thing to cover. We have the Pythagorean theorem. It's another useful thing anytime you have some sort of triangle, and that relates all three side lengths to each other. So we use the trig functions for when we had two side lengths and an angle. This is three side lengths. That says that the hypotenuse squared is equal to the opposite side squared plus the adjacent side squared. Or in math class, you probably learned it as a squared plus b squared is equal to c squared, right? Where the length squared and added of the two shorter sides is equal to the length squared of the longer side. And we will use this often with vectors when we're breaking a long vector into two shorter vectors, or taking the two shorter vectors to combine into a long vector. So Pythagorean theorem is one that pops up quite a bit, as does trig in general. So as you have questions, please ask them. I am happy to help.